Hello everyone, this is Priyanka K studying at Sri Venkateshwara College of Engineering. Today in this video we'll know about properties of groups and subgroups. Introduction to groups and subgroups. A group is a set equipped with a binary operation that satisfies closure, associativity, identity, and inverse properties. A subgroup is a subset of a group that forms a group itself under the same binary operation. In mathematics, group theory is one of the most important branches where we can learn about different algebra concepts such as groups, subgroups, cyclic groups, and so on. As we know, a group is a combination of set and a binary operation that satisfies a set of axioms such as closure, associative, identity, and inverse of elements. A subgroup is defined as a subset of a group that follows all necessary conditions to be a group. Now let's understand the mathematical definition of a subgroup here. Let G and multiplication operator be a group of H be a non-empty subset of G, such as H and multiplication operator is a group. Then H is called a subgroup of G. That means H also forms a group under a binary operation, that is H and multiplication operator is a group. Also, any subset of a group G is called the complex of G. Closure property. The closure property states that for any two elements A and B in a group, their product A B is also in the group. Reflexive closure. The reflexive closure of a relation R on set A is the smallest relation R that contains R and is reflexive. This means that every element in A is related to itself. Formula: R inverse is equals to R union set of A comma A where A belongs to A. Now let's take an example where A is a set of 1 and 2 elements and R is a set of 1 and 2 elements. The reflexive closure of R is R inverse equals set of 1 comma 2, 1 comma 1 and 2 comma 2. Symmetric closure. The symmetric closure of a relation R on a set A is a small relation R inverse that contains R and is symmetric. This means that if A and B belongs to R inverse, then BA belongs to R inverse. Transitive closure. Transitive closure of a relation R on set A is a small relation R inverse that contains R and is transitive. This means that if A B belongs to R and BC belongs to R inverse, then AC also belongs to R inverse. Associative property. According to associative property, when three or more number of groups are added or multiplied, the result, that is sum of the product, remains the same even if the number of groups in a different way. Here, grouping is done with the help of brackets. This can be expressed as A into B or B into C equals A into B into C, and A plus B plus C equals A plus B plus C. Associative property of multiplication and addition is given in the following picture. Now let's go to identity element property. The identity element property states that there exists an element E in the group such that for any element A in the group E, that is A equals E and E equals E. Identity property. The identity property states that when combined with another number in a specific arithmetic operation, the identity element leaves the number unchanged. The property is valid for natural numbers, whole numbers, integers, rational numbers, irrational numbers, and complex numbers. Identity element. The identity element is a specific value that when combined with another number in a special operation or specific operation leaves the number unchanged. Inverse element property. The inverse element property states that for every element in a group, there exists a element that is A minus 1, such that A inverse minus 1 equals A inverse minus 1. A equals V, where E is the identity element. A set has the inverse property under a particular operation if every element of the set has an inverse. An inverse of an element is another element in the set that, when combined on the right or the left through the operation, always gives the identity element as the result. Again, this definition will make more sense once we have seen a few examples. More formally, if x is a variable that represents an arbitrary element in the set where we are looking at, let's call the set we are looking at A. Y represents the special element called the inverse of x. E represents the identity element of a set, and the symbol hash represents our operation. Then, the inverse property for a with the operation hash would be for any element x. There is another element y of the set so that x hash y equals e and y hash x equals e. Now comes the subgroup criteria. Subgroup criteria is defined as a subset H of a group G is a subgroup. If it is closed under the group operation, contains the identity element of G and contains the inverse of its element. The subgroup criteria ensure that H forms a group in its own right and is valid subset of a G. Subgroups can be proper, not equal to the whole group, or improper, equal to the whole group. Types of subgroups. Some common types of subgroups include cyclic subgroups, which are generally generated by a single element, or normal subgroups, which are invariant under conjugation. Subgroups can be classified as a finite or infinite depending on the number of elements they contain. Understanding the different types of subgroups can provide insight into the structure of a group. Now let's see the difference between group and a subgroup. In group, a group is a set of combined with a set. A group is a set combined with a binary operation such that it connects any two elements of a set to produce a third element, provided certain axioms are followed. In subgroup, a subgroup is a subset of a group. H is the subgroup of a group G if it is a subset of G and follows all axioms that are required to form a group. In group, they satisfy the following laws: closure, associative, identity element, and inverse law. In similar in subgroups, they satisfy the following laws such as closure, associative, identity element, inverse law. In group, the number of elements of a finite group is called the order of a group. In subgroup is also a group, uh, and the order of the subgroup is less than the order of a group. Now let's see of an example of a subgroup. Now let G and multiplication operator be a group. A subgroup of G and multiplication operator is a group whose set is a subset of H of G and whose binary operation is the binary operation induced on H by the multiplication operator. We have reverted to a formal notation. The symbols for the binary operation for the group and its subgroups are normally written with the same symbol or with the same additive or multiplicative notation, even though they are technically different functions. We'll continue to use the same symbology for the both operations. Not any subset of G will do. H must be closed under the binary operation of G and multiplication operator, and it must be a group under this operation. To check that H is a subgroup of G, we must ask three questions. Is H closed under G's operation? Is E the H? Is E in the H? If A is any element in H, and also the H element should be in the A inverse also, which is closed under inverses. This is called the three-step verification. As you can know, as you see a two-step and one-step verification, but I preferred the simple ways to check the three key things. A group is a set coupled with the binary operation that connects any two elements of a set to yield the third element. as long as certain axioms are met. A subgroup is a subset of a group that also adheres to the rules needed to form a group. The number of elements in finite group is termed as the order of the group. A group G is set equipped with binary operation, often written multiplicatively, which as an identity inverses and the operation is associative. Not all the subset of H and G are subgroups. In order to be a subgroup, H has to include the identity of G, be closed under inverses and the group operation. Properties of subgroups. Let H be any subgroup of G such that H inverse equals H and double H equals H. H is a non-empty complex of a group G. The necessary and sufficient condition for H to be a subgroup of G is A and B belongs to H, where A B inverse belongs to H, where B inverse is the inverse of B in G. H is a subgroup of G if and only if double H inverse equals H. If H and K are two subgroups of a group G, then HK is a subgroup of G if and only if HK equals KH. If H and K are two subgroups of a group G, then H intersection K is a subgroup of G. The union of two subgroups of a group is a subgroup if and only if one is contained in the other, or if H and G are two subgroups of G, then H union K is a subgroup of G. If and only if H is a subset of K or K is a subset of H. This will conclude the properties of groups and subgroups. Thank you.